Okay, thank you, Abhishek, and I'm happy that that the organizer gave me the opportunity to present our work here. And so this is actually joint work with many people like Thomas Ehrhard and Alexis Saurin, who were my PhD advisor. And during my PhD, I just visited Marcelo Fiore, and Zeinab Galal was actually visiting him in the same time. So we started to work together. So it's a joint work with different people in different times. And okay, so let's move. Okay, so this talk, the idea of this talk is very, very simple, but the talk is a bit more technical. And so I want to say what I'm going to talk today is that basically we have non-well-founded proof theory in linear logic. And so I'm just going to talk about denotational semantic of this logic. But by the way, during the talk, I'm only focused on linear logic. So when I said proof or anything, so I mean proof in linear logic. So I very briefly start by talking about the syntax of circular and non-well-founded proofs in linear logic. And then I will say the categorical axiomatization of the syntax, and then two concrete models. And finally, I try to finish the talk by talking about semantical relationship between the finitary proofs and circular proofs in linear logic. Yes. So, okay. So here is, so I would like to start the talk by saying that why I'm interested in circular proofs. Well, it might be a bit strange because I didn't say what is a circular proofs, but actually my idea at the end of this slide is to say that circular proofs is the thing that satisfy the property that I'm going to say in this slide. So the idea is that I wanted to consider propositional linear logic as a programming languages. But actually, as we know that there is no data types like natural numbers or lists or anything, and consequently we don't have iteration and induction principle in a propositional linear logic. So we might say that, okay, propositional LL is not a reasonable programming languages. And one idea to obtain those data types and recursion or iteration principle is to extend linear logic with a second order quantifier, something like system F by Girard, because once we go to the second order quantifier, we could encode all inductive and conductive data types in the second order linear logic, and then we could do iteration and recursion. But one of the issue is that if you look at this system, so in terms of expressiveness, this system, algorithmic expressiveness, this system is poor. And here is an example that if we try to write a predecessor function in let's say system F or second order linear logic, we will see that it's not possible to write a program that computes this function in a bounded number of reduction steps. So the other idea is to, instead of trying to extend LL with the second order quantifier and do recursion and induction, is to, okay, we can extend it with the data types that we want, like a least and greatest fixed point, that is co-inductive and inductive and co-inductive data types. But again, if we do that, we will see that, okay, we have more or less the same issue as system F. So we cannot write a, let's say, good predecessor function in a finitary LL. And the idea to get rid of this problem is to go to use the circular proofs. And once we go to the circular proofs, we will see that, okay, we could write a good predecessor function there. So that's my personal view. That's why I'm interested in circular proofs, but there are, of course, many others good reason to do circular proofs as well. And but here is why non-well-founded proofs. Again, I didn't say the definition of all non-well-founded proofs, but circular proofs, we could look at them more or less as kind of as kind of defining a function by using a system of equation, or let's say a recursive function. And non-well-founded proofs are like, okay, usually once we are in the logic, when we talk about the proof, we mean finite proof tree. But circular proofs and non-well-founded proofs could be infinite proof tree in depth. And the point is that so if we consider any arbitrary non-well-founded proofs, so that is what I mean by non-well-founded proof theory. And if we consider the one that has a finite representation, those are actually circular proofs. But if we try to do cut-elimination for circular proofs, we will see that this finite representation or this circularity will not be preserved in the limit. So that's why we are obliged to do non-well-founded proof theory as well. And this is not very surprising, I should say, because basically once we extend the logic with the inductive types and induction principle, we don't really have the cut-elimination theorem unless if we want to go to the tight system or like a infinity logic. So I'm not fully sure, but I think this is the same situation as the reason that circularity is not preserved by cut-elimination is more or less the same as the why logic with the induction principle doesn't enjoy the cut-elimination property. Okay. So now let's talk about the syntax of non-well-founded linear logic. So just let me move this tab, sorry. I don't see the title of my slide. Okay, yes. So the non-well-founded linear logic is just an extension of the linear logic with the two new formula, mu zeta A and mu zeta A, that are corresponding respectively for the least fixed point and the largest fixed point. And of course, we also need to extend the syntax of the formula with the type variable zeta as well. So that's at the level of the formula. And for the inference rules, so we have our usual linear logic inference rules. So here is the presentation is, by the way, is in a one-sided sequence calculus. And we just extend it with these two new rules, mu fold and nu fold. And as you see that those rules are very similar, but the point is that we also allow to have a infinite proof trees. So let's look at an example here. Yes. So we could encode the natural numbers, as we all know, by the least fixed point of the formula 1 plus x. And then, so here is the proof or a function from net to net. That is a constants function. And you see that, so we do the neo unfolding, and then we do the linear logic rule Vt. And then on the left-hand side of the proof, it's a finite proof. But on the right-hand side, we repeat exactly the same proof as we have here. So that's what I mean by circular proofs or infinite proofs in general. But the point is that if we do this for free, we could prove anything. Like this is any sequence gamma, and then we do the cut, because actually mu zeta zeta is orthogonal of mu zeta zeta. So it's not exactly the negation, but it's orthogonal. And then on the left side, we do neo unfold forever, and neo unfold on the right side forever. So by this is a proof of any sequence. So we will see that. So we see that it's not a good idea to have to accept everything. And the idea is that people actually started to develop a validity criterion to specify good proofs in order to remove those non-valid proofs, let's say. But I'm not going to talk about this syntactic validity. I'm just focused on semantics here. But I'm almost sure that in the two next slide we will see this syntactic criteria as well. Okay, so that was actually the syntax. So let's move towards the denotational semantic of this syntax that I call mu LL infinity. And so here is a categorical axiomatization of the syntax. Of course, it's not the free constructor. And yes, so here is a definition of a mu LL infinity model. So a mu LL infinity model is just a pair of a silly category of a model of linear logic that I assume is a CPU enriched category. And the second component of this pair is just a basic class of, let's say for the moment, a functor. And then to deal with the context, as we are in a linear logic, we need to assume that, okay, those functors are actually a strong functor. So Ln is just an n-array strong functor from the base category Ln to L. And L0 is just object of the silly category or any model of linear logic in general. And then we need to assume that, okay, this is a closed under composition. And moreover, we also need to assume that we can do all of the linear logic connective tensor with exponential, orthogonal, and everything. And finally, to deal with the fixed point, least and greatest fixed point, we need to assume that, okay, this category, the category of coalgebra over this category has a good property, meaning that it has a final coalgebra and initial algebra. So that's actually axiomatization for interprets, for the moment, interpret proofs and formula of mu LL infinity. And so that's the idea how we interpret formula. So let's say we have a formula A that has a free variable zeta1 to zeta k. So the idea is, basic idea is to interpret this formula as a strong, as a k-array strong functor. And here is just an example for the case of for the case of tensor of the linear logic. So it's that the interpretation is defined by induction. And for the largest fixed point, nu zeta a is we use actually the last point of this definition that we have a final coalgebra. And then we will see that okay, the interpretation of A orthogonal is equal to the orthogonal of interpretation of the A. So that's the idea that very straightforward idea to interpret a formula. But for the proofs, so okay, the general idea is that let's say we have a sequence gamma A1 AN, and yes, and then we have a proof pi of this sequence. So the idea is to interpret this proof as a morphism from one to interpretation of the gamma. But the issue is that okay, we have an infinite proof trees. Usually this definition for the finitary logic is defined by induction on the inference rules. But here the idea is we cannot do the same because we have infinite proofs. But the idea is again very simple. So let's say we have this proof tree. So you cut it at any place you want. So if it is if you look at the position at this red cut, so if it is a usual linear logic rules or it's axiom, we are fine. But if it is something which needs to be continued in the proof trees, we just put omega, and the interpretation of omega is basically the empty set, let's say, or the least element in the category. And then we do all of this cut because this proof is a finite proof. We know how to interpret finite proofs. And then, so this is, we have all of the approximation, and then we just take a supremum of all of them, and we say, okay, that's a definition of interpretation of pi. And the interpretation of mu fold and nu fold, we could say, okay, I know that one needs to be careful about the isomorphism between mu zeta f and f of mu zeta f. But let's say they are equal because actually those are equal in our concrete model. So we could say that the interpretation of pi of the proof of gamma f of mu zeta f is equal to the proof of the sequence gamma mu zeta f, and the same situation for the largest fixed point, and that's the interpretation of the non-well-founded proofs. Then, as usual, so once we have a semantics for the logics, we try to prove the soundness theorem in the sense that if you reduce pi to a pi prime, then actually this reduction step, the semantics should be preserved by these reduction steps. So we have the same result here. But the point is that here, when we say that pi reduces to pi prime, the point is that pi prime could be a limit of an infinite reduction sequence. And to prove the soundness, we need this small lemma saying that if we have a pi I of the Cauchy sequence, then actually the interpretation of the limit of this pi I is actually the lim sup of the interpretation of pi j. And as a corollary, we could prove that if pi reduces to the pi prime by the cut limitation rule of mu ln infinity, even if it's an infinite reduction step, then the semantic is preserved by concatenation procedure. And so yes, okay. So now it's actually a concrete example of this categorical axiomatization. And by the way, here I could say a few words. Okay, one can try to prove other things like adequacy or this kind of other things, but this is not the thing that I would like to talk about today. But that's another work that one can consider. Okay, so the concrete model is actually a very simple model of linear logic. It's a category of sets and relations, rel. And the idea is that we interpret the formula A as a CPO functor from a rel to rel. That's a CPO enriched category. And then here we can usually use we can easily use the result by bond, saying that this CPO functor has both least and the largest fixed points. And then we could see, okay, that's it satisfies the axiomatization, so it's a model of mu LL infinity. But yes, and we see that, okay, if you have a pi of sequence gamma, then the interpretation of pi is a morphism from von to interpretation of the gamma. But one of the issue is that you remember that we don't accept all of the proofs, and we had a syntactic validity, syntactic criterion to distinguish the good and non-good proofs. And the point is that in this semantic realm, I didn't talk about the validity. So any proof, even a non-valid proof, we can interpret it and it works well. And to capture this validity, this syntactic validity criteria, I'm going to use in the semantic, I'm going to use the orthogonality notation in the categorical semantic of linear logic. Okay, so let's try to do some background, very quick background on the orthogonality category, which is introduced by Martin Holland and Andra Schalk in their paper. And so here is a definition. So let's say we have a star orthogonality category L with two objects, one and bottom. And then an orthogonality relation is just a family of subsets of the home sets from 1 to C, and a Cartesian product of the two home sets from the morphism from 1 to C and the morphism from C to bottom. And plus it should satisfy some other condition, and that I'm not going to say them now. And here is the definition of the orthogonality. So if we have an X subset of the home set of the morphism from 1 to C, the orthogonality X orthogonal is defined as follows. So X orthogonal is the all morphism from C to bottom, such that for any element in X, X and Y are related. And dually, we can do the same thing for a subset of the L of C, the morphism from C to bottom. And then here is just a notation of the D of C, and D of C is just basically the whole subset of the home set of L of 1 to C, such that they are bi-orthogonality close. And the last definition that I really needed is we say that this relation, this orthogonality relation, is focus if there is a distinguished subset, we can call it pole, of the subset of L morphism from 1 to bottom, such that this orthogonality relation is basically defined via this distinguished subset. And it will be clear why I would like to focus on a focus orthogonality. And here is another definition from the paper. So focus orthogonality category. So we have a category L, star orthogonality category with a 1 and bottom. And then this category O of bottom of L, the object of this category are pair of C and X, such that C is just basically an object in L, and X is an element in D of C, and D of C is a set of all bi-orthogonality closed subset of the home set from 1 to C. And the morphism from Cx to dy is basically a morphism from C to D, such that it actually preserves this relation, in the sense that if you take an element, a small x in capital X, if you just pre-compose it with F, the result is actually an element in the capital Y. So that's the definition of the focus orthogonality category. And so now the idea is that, okay, we want to interpret mu LL infinity in this orthogonality category. for the LL connective and formula and proofs, we can do exactly what Martin Hyland and Andrzej did. But the question is how we interpret now the least and largest fixed point in this category. And to do that, we are going to consider a vibrational view on this category. Actually, we introduce a vibrational category, and then we interpret those formula in the other category, and we say that, okay, that category is actually equivalent to this orthogonality category. And that's how we interpret this. Okay, so let's look at this focus orthogonality vibrationally. So here is a definition. So yes, yes, L is actually again a startmost category. So here we could define an L index complete lattice. It's just a contravariant functor from L to the poset, the category of complete lattices. And here is the definition of the Gertendie category, that the object of this category are again a pair, that C is actually an element in L, and R is actually an element in that R of C. And remember that R of R, the curly R is just a L index complete lattice. And the morphism is very usual to the definition of the orthogonality category. Is just from CR to DS, or just a morphism from C to D, such that again it preserves this relation in the sense that R is less than or equal of R of Fs, and this less than or equality is actually in the poset category. So now we want to interpret this least and largest fixed point in this yes, in this Gertendie category, and that's the idea. So let's say that we have a functor F from a base category L to L. And then we have this Gertendie category, and then F bar is just a lifting of this functor F, and U is just a forgetful functor, which is a Gertendie vibration. So the theorem is saying that if this functor F below has initial and final coalgebra, then the lifting of this functor F bar has also initial and final coalgebra in this Gertendie category. So in this way, we can actually interpret least and largest fixed point of a mu ln infinity in this Gertendie category. Now let's get back to how this focus orthogonality, this orthogonality category is related to this Gertendie category. So actually, what we can do is that, so if you look at any category L, let's say we also have a pole, subset of the Home-set from one to bottom. And we could see that this actually induces an L index complete lattice. So it induces a contravariant functor from L to poset, and the definition is as follows. So for the object is very easy. So D of C is just a set of whole subset of the Home-set from 1 to C, such that they're biorthogonality rows. And now if we take a morphism F from C to D, we want to see what is a D of F, which is from D of D to D of C. And so D of F of capital Y is all elements, all morphism from 1 to C, such that if we precompose it with F, it's actually an element in Y. So here the point is that we need to prove that this set D of Fy is biorthogonally closed, in the sense that we need to prove it's an element of D of C. And to prove this, actually here is the place that we use the focus orthogonality to prove this. If it is not focus orthogonality, we don't know how to prove it. And then we can see that this Gertendie category is actually isomorphic to the focus orthogonality category. Then we can interpret this mu zeta A and nu zeta A in the orthogonality category. So that's how we interpret formula. And then we can prove this syntactic relation between validity criteria and the semantical notion of the orthogonality. So if we have a model, mu LL infinity model with a pole, and if we have a valid proof pi, which is valid proof of the sequence gamma, the first item is what we saw before. Even if pi is not valid, we have it. But for the second item, we really need to assume that pi is a valid proof. And then we will see that if pi is valid, then its interpretation is actually a morphism, not only in the category L, but in the orthogonality category. Hence, we could say that, okay, this orthogonality category is a model of mu infinity, and that's how we capture somehow the validity, syntactic validity criteria via this orthogonality notion in the semantic. Okay, so let's look at some examples, or maybe one. Yes, one example actually. So here is a concrete example of this orthogonality category. So let's say we have a set E, and then T is just a subset of the power set of the E. And when we define this T orthogonality is all U prime subset of the E, such that it has a non-empty intersection with every element in T. That's the definition of the orthogonality, and actually it's a focus orthogonality. And then we say that T is a totality candidate if it's actually by orthogonality closed. And here is the nice property about this example is that T is actually totality candidate on E if and only if T is a upward close. And like you see that this orthogonality relation is built on top of on the category of rel. But if we do exactly the same thing for other example of model of linear logic like coherence space or other things, we don't have this nice characterization of the biorthogonality via this upward closure. And then here is another notation that tot of X is basically the set of all totality candidates on E, and we could see that this is a complete lattice. Okay, yes, so that's the definition of the non-uniform totality space as a category. So non-uniform totality space is a pair of a set and a totality candidate over that set, like a web of X is a set and T of X is a totality candidate over web of X. And the morphism from X to Y is just a relation from the underlying set X to the underlying set Y, such that it preserves the totality relation in the sense that if you take an element in T of X, and if you apply this functional relation, this dot means a functional relation, T dot U is actually an element of the totality candidate over Y. And we could see that this knot is actually a focus orthogonality category, that this pole is basically the singleton set identity, and hence it's a model of mu infinity. So we can interpret proofs and formula in this knot, and we can capture the validity in the knot. Okay, so here is some application of the knot. So let's say we have a Boolean type in linear logic 1 + 1. The point is that now let's take a proof pi of 1 + 1. By the result that we have, we could see that interpretation of pi is actually a totality in the interpretation of 1 + 1. And if we look at now the totality candidate over the interpretation of 1 + 1, we will see that empty set is not there. So if we have a proof pi of Boolean 1 + 1, we see that, okay, this interpretation is non-empty. So we could see that, okay, pi is actually either true or false. So we see the value. We could somehow prove a syntactic pre-proof of the fact that any term of the Boolean has actually a value at the end of the day. And here is another example of this application of this model, this concrete model. So this is the type of the stream of integer. Sigma is equal to mu zeta of nat tensor zeta. And now the point is that if we take this definition as a definition of the type of a stream of integer, we could prove that there is no proof of pi of sigma orthogonal nat, in the sense that we cannot extract actually the integer from the stream. And to prove this theorem, it's very easy. So we assume that we have such a proof, and then we look at the interpretation in the interpretation of this proof. It should be a morphism from sigma to nat, and if we say that if we apply it on an empty set, we take an empty set, but we know that empty set is not actually a totality candidate in the natural numbers. So that's a contradiction, and we don't have such a proof. And to just have a better type, the encoding of the type of stream of integer, we could actually do this one with nat tensor zeta to get rid of this emptiness of the interpretation of sigma. And so I think I need to be more quick. So I'm just would like to say a few things about the relationship between the finitary proofs and circular proofs. So here is the thing. So that's an easy direction. Like any any finitary proof in linear logic can be actually translated to a circular proofs, and that's a very easy translation. And we can prove that okay, this translation is the semantic is preserved by this translation. So this translation is not only at the level of probability, but it's also at the level of proof theory. And there is also another transformation in the reverse direction for a fragment of circular proofs of mu L infinity, not, of course, not for the moment, all circular proofs. That is developed by David Ballham and Alexis Saurin in the paper. And we could also prove that, okay, the semantic is also preserved by this reverse transformation. So let me try to conclude. So yeah, so here are some future directions. The first thing is that, okay, we saw some semantics of non-well-founded proofs. We could, of course, interpret circular proofs, because circular proofs are just an example of non-well-founded proofs. But the point is that we didn't use the fact that those are circular. So we just look at the circular proofs as non-well-founded proof and we interpret it. So then the question is, can we just provide semantic, especially for circular proofs? So that's the first thing, a categorical axiomatization, I mean. And to do so, we could consider the work by Luigi Santacanolo that he did a categorical semantic only for circular proofs, not non-well-founded proofs, in a very small fragment of linear logic, like additive linear logic. And so we still don't know how we can actually extend this to the multiplicative additive linear logic. And there is also another sort of semantics by Gianluca and Anupam, and I think I'm sure he will discuss it today. It's kind of a realizability semantic for mu-mal, for other logic as well, but I just mentioned it for mu-mal here. And the interesting question that I would like to understand is that, so we could take their semantic, because their semantic is basically their interpret proofs as kind of function, let's say lambda calculus. And then we could interpret those functions in some domain theoretical, let's say some coherence model or any model of the lambda calculus. So that's actually, we could say it's an indirect interpretation of the mu-mal in some domain theoretical model. And then I would like to understand what is the difference or what is the relationship between this indirect semantic or the direct semantic that we have for mu-mal. And the last question that is the fact that we really need to assume that the orthogonality relation is focused. Otherwise, I don't know how to complete the proofs. And so the question is how we should deal with the non-focused orthogonality, like finiteness space. It's actually an example of the non-focused orthogonality of model of linear logic, and I don't know how to deal with those. And I am done. Thank you. I can't hear you if you are saying something.
Yeah, I will repeat the questions to you, Father.
Yeah, but by the way, sorry, I don't know if you heard this, the sound of music here. It's a fed the music here, and I'm sorry for that.
Okay. So as I understood it, the main result here is that you have a valid proof, then its semantics gives a morphism in the orthogonality category. However, if there's some sort of completeness counterpart to that, if you have a pre-proof and its semantics gives a morphism in the orthogonality category, then is it necessarily a valid proof? So Farzad, the question is that you have some sort of completeness. For example, like the soundness part was, if your proof is valid, then you have a morphism in the orthogonality category. Does it make sense to have completeness? Do you have something like that?
I think it definitely makes sense, but this is not true in the case of the not. Like there are total morphisms that are not valid proofs, and I think it's not very easy to capture the syntactic validity in order to have a completeness result. But it definitely makes sense. It will be quite useful, but it's not the case for all the models that I know.
Maybe you get a better, more general general notion of syntactic ability. This question regarding the vibration, and there's something called complete static vibration. It's very similar to relation vibration. So with your definition of relation vibration is that indexing the preserve do you need this requirement in the proof of
Okay, I'll try to summarize that. Harsh has a question on models of coalgebraic modal logic and if there's a connection with that and in your specifically in your proof of soundness.
Sorry, if there is a connection between what and what?
Coalgebraic modal logic.
Coalgebraic?
If you can comment, ask a question, that would be amazing. Yeah.
Are you trying to write the question? Okay. Yes.
The question is, I mean, in coalgebraic modal logic, we have also complete lattice vibration, that people call it C-lat vibration. And the difference between your relation vibration is that you also require that the reindexing preserves arbitrary mean. And I was wondering whether this requirement you need in the proof of existence of final coalgebra.
Sorry, can you just repeat the requirements again?
That the reindexing preserves the arbitrary means.
Yes, yeah, definitely. Yes, definitely. This we really require it, like basically to prove that this lifting has a final and initial algebra. We need to assume this, and yes, absolutely, and that's actually why we consider this L-index post-sets notion.
Okay, but you do need this condition. You do
Sorry?
require this condition. You do require this condition.
Yes, yeah, absolutely, yeah.
Thanks.
Thank you, Farzad. We'll move on to the next.
Yeah, thank you.